So, consider a reaction for the dissolution of ammonium nitrate. So, NH4NO3 solid goes to NH4 plus aqueous plus NO3 minus delta H value is given plus 25.1 kilojoule per mole, and delta S is also given 105.7 joules per Kelvin per mole. Determine the change in entropy of the surroundings of for a reaction at 25 degrees Celsius and use this to predict whether the reaction is spontaneous or not. So, the value of delta H is given. So, delta H for this reaction is plus 25.1 kilojoule per mole. So, delta H surroundings will be opposite of this. So, sign will be reverse, so minus 25.1 kilojoule per mole. So, we know that delta S surroundings will be delta H surroundings by T. So, you get minus 25.1. So, it is in kilojoule. So, we can convert into joule. So, this is joules per mole, and temperature is 25 degrees Celsius. So, T is 25 degrees Celsius, means 298 Kelvin. So, this is 298 Kelvin. So, if we do it, we get the value minus 84.24 joules per Kelvin per mole. So, delta S surroundings is given and delta S system is also given, is 105.7 joules per Kelvin per mole. So, delta S total, because in order to see whether a reaction is spontaneous or not, if the process is not isolated one, so we need to calculate delta S system and delta S surroundings separately. That is what we did it here. So, delta S surroundings value is minus 84.24 and delta S system is that is minus delta 84.24 and delta S system is plus 105.75. So, clearly delta S total will be positive here. So, delta S total will be your delta S surroundings plus delta S system. So, delta S surroundings value is minus 84.24 and delta S system is 105.7. The unit is joule per Kelvin per mole. So, if we do it, we get the value 21.46 joule per Kelvin per mole. So, this is plus sign. Okay, so, delta S total, since delta S total is positive, so the dissolution of ammonium nitrate at 25 degrees Celsius is spontaneous. Next, we move to problem number 14, which says, given that the standard enthalpy change for the phase transition of liquid water to steam is 50.8 kilojoule per mole at 373 Kelvin, calculate the entropy change associated with the vaporization of water. Okay, so, delta H value, so liquid water to steam, so heat has to be given here. So, delta H value is positive here. So, the value of delta H transition, so phase transition is taking place here. So, delta H transition is 50.8 kilojoule per mole, and T transition, so transition temperature, T transition is transition temperature, means the temperature at which the phase transition is taking place. Here it is 373 Kelvin. So, delta S transition, we know delta S transition. So, entropy change associated with this transition process is delta H transition by T transition. So, delta H transition we know 50.8 kilojoule, it is given in kilojoule unit. So, we need to convert this into joule unit. So, 50.8 times 10 to the 3 joules per mole, and the value of T transition is 373 Kelvin. So, if we do it, we get the value of 136.19 joule per Kelvin per mole. So, this is problem number 14. Next we move to problem number 15. It says, given the enthalpy of vaporization of liquid diethyl ether as 36 kilojoule per mole at its boiling point of 35 degrees Celsius. Calculate the entropy change for the conversion from liquid to vapor and the conversion from vapor to liquid. So, if we consider first the conversion of from liquid to vapor. So, for the conversion from liquid to vapor, so delta H is plus. So, heat has to be provided. So, kilojoule per mole. So, if we convert it into joules, we get 36 times 10 to the 3 joules per mole. And T transition is also given. T transition is 35 degrees Celsius, means 308 Kelvin. So, delta S transition, so this is delta H transition actually. So, delta S transition for liquid to vapor. So, liquid to vapor is delta H transition by T transition. So, we get 36 into 10 to the 3 by 308 joules per mole per Kelvin. So, if we carry out this one, we get the value of 116.8 joules per Kelvin per mole. So, this is the change in entropy when the conversion is taking place from liquid to vapor. Now, if we do the conversion from vapor to liquid, so for the conversion of vapor to liquid, the system here, system is liquid diethyl ether or diethyl ether. So, system has to release heat. So, delta H transition will be negative here, is negative of delta H vaporization. So, minus 36 kilojoule per mole. So, you get 36 times 10 to the 3 joules per mole, minus sign. So, again T transition is 35 degrees Celsius. So, we get 308 Kelvin. So, delta S transition for vapor to liquid will be minus 116.8 joule per Kelvin. This was problem number 15. So, problem number 16 says delta H and delta S for the reaction Ag2O goes to 2 Ag plus half O2 are 25.56 kilojoule per mole and 5.60 mole per Kelvin respectively. Determine the temperature at which the Gibbs free energy change for the reaction becomes 0. Also explain the direction of the reaction will take at this temperature and at temperatures lower than this, and justify the reasoning. So, we know delta G is delta H minus T delta S. Now, value of delta G and delta S are given. So, delta H and delta S are given. So, delta H is 25.56 kilojoule per mole. So, if we convert into joule, or if we keep it like this, we will convert this delta S times T is in kilojoule. So, delta S here is 5.60 joules per Kelvin per mole. So, delta G is 25.56 minus, okay, so no, temperature we need to calculate. So, T times 5.60 times 10 to the minus 3, if we convert into kilojoule units. So, delta G has to be 0. So, 0 is 25.56 minus T times 5.60 times 10 to the minus 3. So, value of T will be 25.56 divided by 5.60 times 10 to the minus 3. So, the value we will be getting is 4564.3 Kelvin. So, this is the temperature at which delta G is 0. So, temperature at which delta G is 0. This is the first part. The second part is also explain the direction of the reaction will take at this temperature and at temperatures lower than this. So, at this temperature reaction is in equilibrium. Okay, so, since delta G is 0 at 4564.3 Kelvin temperature, so the reaction is at equilibrium. Now, if we decrease the temperature, so since this is the threshold temperature, minimum temperature at which you get the value of delta G is 0. So, this is the minimum temperature. If we increase the value of T, so when T is greater than 4564.3 Kelvin, then delta G is negative, right. If we substitute it here you can see that if the value of T is greater than 4.64.3 Kelvin, then delta G is negative. So, below this temperature and when T is less than 4564.3 Kelvin, then delta G is positive, is greater than 0. So, it says, so for when delta G is less than 0, so the direction of the reaction is in the forward direction. And when temperature is lower than 4.64.3 Kelvin, then delta G is greater than 0. So, the reaction or the reverse reaction is favorable, or in the other hand the forward reaction is not favorable. The forward reaction is not favorable. Then we move to next question, next problem, problem number 17. It says for the reaction CO plus half O2 goes to CO2 at 300 K. Determine if the reaction is spontaneous and specify whether it is exothermic or endothermic. You are given that the standard entropy change is minus 0.094 kilojoule per mole per Kelvin, and the standard Gibbs energy of formation for CO2 and CO are minus 494.4 kilojoule per mole and minus 237.2 kilojoule per mole respectively. So, what will be the delta G for the reaction? Okay. So, delta G Gibbs energy of formations are given. So, delta G reaction will be, so delta G reaction, it is in the standard state. So, we can write naught here. So, delta G and naught is delta G are not products minus delta G are not reactants. So, what will be the value of delta G naught? So, what is the product here? Product is CO2. Okay. So, value of delta G naught for CO2 is minus 494.4 and delta G naught for CO is also given is minus 237.2. So, the unit is kilojoule per mole. So, if we do it, we get minus 257.2 kilojoule per mole. This is a delta G naught. Okay. So, delta G naught of reaction. So, we know delta G is delta H minus T delta S. So, delta G naught is delta H naught minus T delta S naught. Now, what is the value of T? So, T is 300 Kelvin. Okay. So, what is the value of delta G naught here? So, delta G naught is minus 257.2 in kilojoule per mole unit. Delta H naught we need to calculate, minus T is 300 times delta S naught value is also given minus 0.094. So, if we calculate this one, we get delta H naught value of delta H naught. So, value of delta H naught is minus 285.4 kilojoule per mole. So, delta H naught here is negative. So, the reaction is exothermic process, exothermic one. The reaction is exothermic. We move to problem number 18. It says, what will be the entropy change of the system when 1 mole of a gas expands from 2 liter to 4 liter under isothermal conditions. Okay, so, we know delta U is Q plus W, right. Now, isothermal condition. So, delta U is 0 here. So, delta U is 0 for isothermal process, and we consider here ideal gas and ideal gas. So, it says Q is minus W, and the process, if the process is reversible, we consider reversible process here. So, we get W reversible is N at T minus N at T ln Vf by Vi. So, we get Q reversible is N at T ln Vf by Vi. So, Vf is the final volume and Vi is the initial volume. So, here Vf is the final volume and Vi is the initial volume. Now, if we divide both sides by temperature T, we get Q reversible by T, and Q reversible by T is minus NR ln Vf by Vi. Now, Q reversible by T is nothing but change in entropy, that is delta S is NR ln Vf by Vi. Now, number of moles here, number of moles N is 1, right, and Vi is 2 liter, Vf is 4 liter. So, we get delta S is 1, value of R is 8.314 in joule unit. So, ln 4 by 2. So, if we do it, we get delta S is 5.76 joule per Kelvin. Okay. So, this is the value of change in entropy. We move to problem number 19. It says a reversible engine operates between two temperatures with a temperature difference of 10 degrees Celsius. If the engine absorbs 856 joules of heat from its source and releases 636 joules of heat to its sink, determine the temperature of both the source and the sink. Let the temperature of the source be T1 and the temperature of the sink be T2. So, T1 minus T2 is 110 degree Celsius, means 110 only. So, efficiency eta, we know 1 minus T2 by T1. So, we get 1 minus Q2 by Q1. Okay. So, or you can write eta is T1 minus T2 by T1. Now, T1 by T2 is Q1 by Q2. Okay, so it gives T1 by T2 is 856 by 636. So, it gives T2 by T1 is 636 by 856. And T1 minus T2 value is also we know. So, this is your 110. So, if we substitute those things here, so we get eta is 1 minus 636 by 856. So, it gives you 220 by 856. So, that is this is the value of eta, and this value of eta we will substitute here. So, we get 220 by 856 gives you 110, because T1 minus T2 is 110 by T1. So, we get value of T1 is 110 times 856 by 220. So, we get 428. So, 428 K. So, this is temperature of the source. So, T2 is 428 minus 110, so 318 K. Thus, the temperature of the source is 428 K, and the temperature of the sink is 318 K. We move to problem number 20. It says a system has heat capacity Cp. So, Cp here is not constant, it is function of temperature A plus Bt, where A is 20 joule per Kelvin per mole and B is 0.05 joules per Kelvin per mole. Calculate the entropy change when 1 mole of this system is heated from 300 Kelvin to 800 Kelvin. So, we know delta H is Qp is Cp dt, right, and delta H by T is delta S. So, if we combine these two, we get T delta S is Cp dt. So, we get, okay, this is delta T, not dt, this is delta T. So we write delta S is Cp times delta T by T, and when the difference is very small, this is for finite difference. So, we write ds is Cp dt by T. Now, if we integrate it both sides, so integration, so you get S1 to S2. So, for S1 the temperature is 300 K and for S2 the temperature is 800 K. So, ds is integration 300 to 800 Cp dt by T. Now, Cp is not a constant term here, it depends on temperature. Had it been constant, so we would have taken Cp out of the integration side, but since Cp is not a constant term here, so we need to substitute the value of Cp here. So, 300 to 600, 800 limit, and then A plus Bt times dt by T. So, we get S2 minus S1 is integration of 300 to 800. A is constant now, so A by T dt plus 300 to 800 B dt. So, you get delta S is A ln T 300 to 800 plus B T 300 to 800. Now, if we substitute the value, so delta S is A and the value of A is given 20. Okay, so 20, and then you get ln 800 by 300 plus B 800 minus 300. So, value of B also you can substitute it here. So, value of B is 0.05 times this. So, you get delta S is 20 ln 2.667 plus 0.05 times 500. So, if we further carry out, we get delta S is 44.616 joules per Kelvin, and then per mole. Okay, so this is the value of delta S. Next we go to problem number 21. Which of the following changes will increase the efficiency of a Carnot engine operating between a source and sink, raising the temperature of the source? What is the expression for efficiency of a Carnot engine? So, the efficiency of Carnot engine can be expressed as eta is 1 minus T sink by T source. Now, if we raise the temperature of the source, so the denominator will increase here. So, this quantity, if we keep the temperature of the sink constant and if we increase the temperature of the source, so this value becomes smaller, so eta will increase. So, A is correct. Option A is correct. When T sink is fixed or constant. And lowering the temperature of the sink, this will also work. So, if we lower the temperature of the sink, so this quantity T sink by T source will become smaller. So eta will increase. Okay. So, B is also correct. When T source is fixed. That is both raising the temperature of the source and lowering of the sink. So, if we raise the temperature of the source as well as if we lower the temperature of the sink, then it will decrease or it will increase the eta value by quite considerably, right. So, C is correct. And then D is not correct. Lowering the temperature of the source, if we lower the temperature of the source, so this quantity T sink by T source will become high or higher. So eta will become smaller. Okay, so D is not correct, provided T sink is constant. So, A, B, C, both these three are correct. A, B and C are correct. Next we discuss problem number 22. It says an engine operates with a coal reservoir at 300 Kelvin, has an efficiency of 0.30 and absorbs 500 joules of heat during each cycle. What is the amount of work the engine performs in each cycle? How much heat energy does the engine release to its coal reservoir per cycle? Also find the temperature of the source. So, value of eta is given and value of sink is given. Okay. So, here efficiency eta is 0.30 and temperature of reservoir is T2 is also given. This is 300 Kelvin. Okay, and heat absorbs is 500 joules. This is also given. This is value of QH. So, eta is W by QH, we know. for a Carnot cycle, eta is W by QH. So, you get W is QH times eta. So, value of QH is 500 times 0.3. So, we get 150 joules. This is the first part. Okay, what is the amount of work done? Okay, so this is the amount of work done each cycle. Amount of work done, or amount of work the engine performs. Each cycle. Next question is, how much heat energy does the engine release to its cold reservoir per cycle? Okay, so heat released to sink, heat released to sink, if we say this is QC, is QH minus W, right? So, value of QH is given, so 500 minus W is 150, so we get 350 joules. And part C is very easy. Okay, also find the temperature of the source. So, eta we know efficiency eta is 1 minus T2 by T1. Here T1 is the temperature of the source. So, value of eta is given 0.3 and 1 minus T2 is also given, T2 is 300. So, we need to calculate T1. So, we get 300 by T1 is 0.7. So, we get T1 is 428.57 Kelvin. So, the temperature of the source is 428.57 Kelvin. Next, we move to problem number 23. It says an ideal gas at a temperature of 300 Kelvin undergoes a reversible isothermal compression so that its final volume becomes 1/5 of its initial volume. What is the entropy change? This is very similar to the problem we discussed before. So, we already discussed delta S is NR ln Vf by Vi, where for isothermal process, isothermal reversible or isothermal process. Now, Vf is initial final volume, and Vi is the initial volume. So, the problem is the final volume becomes 1/5 of its initial volume. So, Vf is Vi by 5, right. So, delta S is N we consider 1 mole. Okay, so, we considering 1 mole, means N equals to 1. We write 1 times 8.314 ln Vf is Vi by 5 by Vi. So, we get delta S is minus 13.38 joules per Kelvin. The value of delta S will be minus here because the compression is taking place. So, volume decreases here. So, randomness will decrease. So, the final volume will become lower than the initial volume. So, final entropy is lower than the initial entropy. So, we get delta S is negative. Problem number 24 says what is the entropy change of 10 gram of steam at 100 degrees Celsius when it condenses to water at the same temperature. Latent heat of vaporization is given. So, steam goes to liquid water. So, steam. So, vapor to liquid transition. So, LV, latent heat of vaporization, this is nothing but delta H transition. It will be negative. So, minus 22.26 times 10 to the 26, sorry 10 to the 6 joules per kg. Okay. And so, the heat required or heat released here by 10 gram of steam, 10 gram of steam is minus 2.26. So, 10 gram is 10 times 10 to the minus 3 kg. So, minus 2.26 times 10 to the 6 times 10 times 10 to the minus 3. This is in joule unit, this is in joule. Now, T transition is 100 degrees Celsius. So, 373 Kelvin. So, delta S transition is delta H transition by T transition. Now, delta H transition, this is the actual delta H transition, this is your delta H transition, okay, is minus 2.26 times 10 to the 4 by 373 joules per Kelvin. Okay, so if we do it, the value will be here minus 60.6 joule per Kelvin. We move to problem number 25. It says a metal rod is used to transfer heat between two heat reservoirs at temperature Th and Tc. If an amount of heat Q moves through the rod from the hot reservoir to the cold reservoir, what is the total entropy change for the metal rod, the hot reservoir, the cold reservoir and the entire universe? So, the temperature of the source here is the temperature of the source is Th. Temperature, the temperature of the sink is Tc. So, heat flows from hot reservoir this is Q and the hot reservoir, therefore, the hot reservoir or source loses heat Q. So, delta S of hot reservoir is Q by Th, and we will have minus sign here because his reservoir is losing heat here. So, entropy change of the entropy change of cold reservoir is, we say this is delta SC is cold reservoir is gaining heat. Positive sign because the cold reservoir is gaining heat. The rod simply conducts heat at steady state. So, delta S rod will be 0. So, entropy change of the universe is delta S is delta SH plus delta SC plus delta S rod. Now, if we substitute these quantities, we write Q 1 by Tc minus 1 by Th, and delta S rod is anyway 0. Now, since Th is greater than Tc, so it says 1 by Tc is greater than 1 by Th. So, delta S universe, we write this one is delta S universe. Delta S universe. So, delta S universe is greater than 0 or positive. Next problem is, suppose you place 50 gram of ice at 100 degree in contact with a heat reservoir maintained at 20 degrees Celsius. So, ice we are putting 0 degree to a reservoir to 20 degrees Celsius. Heat moves from the reservoir to the ice, causing it to melt and then warm up until it reaches 20 degrees Celsius. Calculate the total change in entropy of the ice during this process. So, we have for first solid ice, it takes heat, solid at 0 degrees Celsius. So, it takes heat and then it converts into 0 degrees Celsius liquid water, and then from 0 degrees Celsius liquid water the temperature increases to 20 degrees Celsius of liquid water. So, we need to calculate delta S for two processes, one for the phase transition means 0 degrees Celsius ice to 0 degrees Celsius liquid water, and then another from delta S for the increase or for the change in temperature from 0 degrees Celsius liquid water to 20 degrees Celsius liquid water. So, here LF is given 3.34 times 10 to the 5 joules per kg. Now, what is the weight of the ice? Ice is 50 gram. So, heat required. Okay, so heat required to melt 50 gram or 50 times 10 to the minus 3 kg ice at 0 degrees Celsius to 50 gram of liquid water at 0 degrees Celsius is 3.34 times 10 to the 5 times 50 times 10 to the minus 3 in joule unit. So, we get 3.34 times 5 times 10 to the 3 joules. So, this is delta H transition. Okay. So, delta S transition, this is nothing but delta H transition, and this is positive quantity as the transition is taking place from solid to liquid, solid ice to liquid water, to liquid water. So, delta S transition for solid to liquid, we get 3.34 times 5 times 10 to the 3, and T transition is 0 degree Celsius. So, 273 Kelvin by 273 Kelvin. So, if we do it, we get 61.2 joules per Kelvin. This is 20 Kelvin, this is joule, so joules per Kelvin. Now, we got liquid water. Now, we need to increase the temperature of liquid water. Okay. So, delta S2 or delta S for temperature 273 Kelvin to 293 Kelvin is m c ln Tf by Ti. Now, here Ti is 0 degree Celsius or 273 K, and Tf is 20 degree Celsius or 293 K, and m is 50 grams. So, 50 times 10 to the minus 3 kg, and C is given in kg. So, 4186, this is joules per kg per Kelvin, and ln 293 by 273. So, if we do it, we get 14.8 joule per Kelvin. You see, in both cases delta S is positive. It has to be because one from solid ice to liquid water. So, randomness increases if we move from solid to liquid, and another is temperature increases. So, with increasing temperature, randomness increases. So, in both cases we get delta S positive. So, delta S total for this process is delta S transition for solid to liquid plus delta S when temperature increases 273 Kelvin to 293 Kelvin. So, we get 61.2 plus 14.8 joules per Kelvin. So, we get 76 joules per Kelvin. Problem number 27 says a cylinder initially contains 500 gram of helium at 128 atmospheric pressure and 20 degrees Celsius. Because the valve is leaky, all the gas slowly escapes isothermally into atmosphere. Assume 1 atmosphere. What is the entropy change for the gas resulting from this process? So, what is the number of moles? Okay, the molar mass or the atomic mass here, the atomic mass of helium is 4 gram, right? So, the number of moles of helium is 500 by 4, it's 125. Okay, so isothermal expansion, for the isothermal expansion, P1 is 120 atmosphere and P2 is 1 atmosphere, and T is 20 degrees Celsius, so 293 Kelvin. So, we know delta S change in entropy is nR ln V2 by V1. Now, at a constant temperature, means isothermal process, and when number of moles N is also constant, P is proportional to 1 by V, right? That we know. Okay. So, or we can write V is proportional to 1 by P. So, pressure and volume, they are inversely proportional. So, we write delta S is NR ln P1 by P2. So, we get delta S is N is 125, R is 8.314 in joule unit, and ln 120 by 1. So, if we do it, we get delta S gas, write gas here, is 4980 joules per Kelvin. Problem number 28 says a redox reaction at 298 K has the following properties. So, standard enthalpy change is given, standard entropy change is also given. The reaction has a stoichiometry that involves transfer of 2 moles of electrons per mole of reaction. Calculate delta G naught at 298 K. Is the reaction spontaneous under standard conditions? If not, calculate the minimum temperature at which the reaction becomes spontaneous. So, delta H naught is given here. So, delta H naught is plus 110.0 kilojoule per mole. So, we can write 110 times 10 to the 3 joules per mole, and delta S naught is 300 per Kelvin. So, delta G naught is delta H naught minus T delta S naught. So, we write 110 times 10 to the 3 minus temperature is 298. So, T is 298 K. So, 298 times 300. So, if we do it, we get 20.6 kilojoule mole to the minus 1. Since delta G is greater than 0, the reaction is not spontaneous, Okay. For the reaction to be spontaneous, delta G has to be less than 0. When delta G equals to 0, reaction is at equilibrium. Okay. So, the minimum temperature, at which the reaction attains equilibrium is T is, so delta G is 0. So, delta G is 0 at equilibrium. Is delta H naught, delta G naught if I say, so delta H naught minus T delta S naught, T delta S naught. So, the minimum temperature or the temperature at which the reaction reaches equilibrium is delta H naught by delta S naught. So, this is 110 times 10 to the 3 by 300. So, if we do it, we get 366.7 Kelvin. So, so this is the minimum temperature. So, the temperature has to be more than 366.7 Kelvin for the reaction become spontaneous. At 366.7 Kelvin, the reaction is at equilibrium as delta G naught is 0. Okay, thank you.